Section: Introduction. In this section, we discuss the advancements in artificial intelligence over the past decade, particularly through the use of deep neural networks, which have proven effective in a wide range of challenging applications. However, we recognize that there are still significant challenges and limitations in data science, especially in fields that require specialized knowledge and advanced coding skills, such as biology, healthcare, and business. One major issue we face is the lack of effective communication between domain experts and complex AI models. To tackle this problem, we introduce LAMBDA, an open-source, code-free multi-agent data analysis system that aims to bridge this gap. Our goal with LAMBDA is to create a platform that promotes smooth interaction between domain expertise and AI capabilities in data science. We have outlined several key objectives for developing LAMBDA. A. Overcoming the coding barrier. We understand that coding can be a significant hurdle for domain experts who do not have a background in computer science. LAMBDA addresses this by allowing users to communicate with data agents using natural language instructions, providing a coding-free experience. This approach makes data science tasks, like data analysis and mining, more accessible and efficient for professionals from various fields. B. Merging human intelligence with AI. The current data analysis landscape struggles with the absence of an effective intermediary that connects human expertise with artificial intelligence. AI models often lack the necessary domain knowledge for specific tasks, while domain experts find it difficult to incorporate their insights into AI models to improve performance. LAMBDA offers a solution by providing well-designed interface templates that allow agents to access external resources, such as algorithms or models. This integration ensures that domain-specific knowledge is utilized effectively, enabling customized data analysis and improving the agent's ability to perform complex tasks accurately. C. Transforming data science education. We believe that LAMBDA has the potential to revolutionize data science education. It provides educators with the flexibility to customize their teaching plans and incorporate the latest research findings seamlessly. This adaptability makes LAMBDA an essential tool for educators aiming to deliver innovative and personalized learning experiences, setting it apart from direct applications of models like GPT-4. Additionally, we have designed LAMBDA to be reliable and portable. Reliability means that LAMBDA can consistently and effectively handle data analysis tasks, while portability ensures compatibility with various large language models, LLMs, allowing LAMBDA to be enhanced by the latest advancements. To save users time on tasks like report writing, we have also included automatic analysis report generation. While GPT-4 has shown impressive performance in advanced data analysis, its closed-source nature limits its adaptability to the evolving needs of data science and specialized education. Moreover, there are concerns about data privacy and security with GPT-4. In contrast, LAMBDA, being open-sourced, alleviates these privacy concerns while offering greater flexibility and ease in integrating domain knowledge, installing packages, and utilizing computational resources. We have observed that LAMBDA performs exceptionally well on various machine learning datasets, achieving notable accuracies of 100%, 98.07%, and 98.89% on the NHANES, breast cancer, and wine datasets, respectively. In summary, the main features of LAMBDA include 1. A coding-free and natural language interface, 2. Integration of human intelligence and AI, 3. Reliability, and 4. Automatic analysis report generation. This paper begins with a background and foundational overview in the first section. The second section details the methods we propose for LAMBDA. To assess its effectiveness, we present our experiments and results in the third section. Additionally, the fourth section illustrates case studies of LAMBDA in various scenarios, including data analysis, human intelligence integration, and interactive education. We conclude with a summary in the final section. Supplementary materials, such as initial ideas, prompts, case studies, and experimental settings, are included in the appendix. In recent years, we have witnessed rapid advancements in large language models, LLMs, which have opened up new possibilities in artificial intelligence. Examples of LLMs include GPT-3, GPT-4, PaLM, LaMBDA, and Qwen. These models excel at understanding, generating, and applying natural language. As a result, LLM-powered agents have been developed to automatically address problems across various domains, including search engines, software engineering, gaming, recommendation systems, and scientific research. These agents often utilize a chain-of-thought approach and have the ability to use tools like APIs, code interpreters, and retrievers. These developments have inspired us in designing LAMBDA, particularly in the areas of function calling and code interpretation. Section Summary. In this section, we introduce LAMBDA, an open-source, code-free multi-agent data analysis system designed to bridge the gap between domain experts and AI models, enabling users to interact with data through natural language and enhancing accessibility in data science. LAMBDA also integrates human intelligence with AI, reshapes data science education, and ensures reliability and portability, while addressing privacy concerns and demonstrating superior performance on various machine learning datasets. Section: Enhancing LLMs with Function Calling. In this section, we explore how we can enhance large language models, LLMs, through function calling. Function calling refers to the ability of LLMs to utilize external APIs or tools to perform tasks based on their specific functions. The process works like this. First, we classify the user's request into functions using function annotations. Next, we execute the chosen functions, and finally, we generate an answer based on the results of that execution. We examine the current state of tool learning with LLMs and highlight its progress in various applications, including programming, calculators, and weather inquiries. However, we believe that the function calling method may struggle in data science scenarios due to a couple of key issues. First, we suspect that many APIs in data science have intricate relationships and lengthy annotations. These extensive details might create sequences that exceed the ILM's maximum processing capacity, which could lead to the loss of important API information and user messages. Second, we think that as the number of APIs increases, the model's ability to accurately select the right API diminishes. This complexity can result in incorrect tool choices, which directly impacts the accuracy of the results. Next, we discuss how we can empower LLMs with code interpreters, allowing them to execute code and obtain results. We demonstrate the capabilities of a code interpreter in ChatGLM, which facilitates programming tasks like complex calculations and figure drawing. We have effectively used the code interpreter to solve mathematical problems, achieving notable advancements. However, we recognize that the code involved in data science problems is often more complex than in other areas. If we cannot ensure the correctness of the code, the reliability of the code interpreter will be compromised. To tackle this challenge, we propose a self-correction mechanism that allows our agent to learn from its mistakes, thereby enhancing reliability. We also delve into the concept of multi-agent collaboration. A multi-agent system consists of several autonomous agents that work together in planning, discussions, and decision-making, similar to how humans collaborate in problem-solving tasks. Each agent has unique skills, goals, and perspectives, and they can operate independently or as a team to address complex challenges. We present an agent system designed like a software company, featuring agents such as programmers, code reviewers, and test engineers, which can complete the entire software development process in under 7 minutes. Additionally, we introduce an agent hospital that simulates the complete process of treating illnesses, achieving impressive results in managing respiratory diseases. Our LAMBDA system also simulates real-world data science workflows through the collaboration of multiple agents, which enhances system stability. We then discuss Retrieval Augmented Generation, RAG, a technique that retrieves external sources to improve the accuracy and reliability of LLM responses. In this method, resources are divided into smaller vector fragments and stored in a vector database. RAG first queries this database to find document fragments that are relevant to the user's query by measuring similarity. These fragments are then used to improve the accuracy of the responses generated by the LLMs. This approach is particularly useful for incorporating external knowledge and reducing inaccuracies. However, we find that the standard RAG workflow may not perform well in certain data science contexts. For instance, the user's instructions and the relevant code fragments might not show significant similarity, leading to inaccurate searches. Additionally, the varying lengths of code fragments can affect the search results. For example, customized optimization algorithms often have lengthy code, making it difficult to match complete and correct code fragments. To address this, we have designed a knowledge base called KV to integrate human intelligence into our AI system. In our methodology, we present our multi-agent data analysis system, LAMBDA, which consists of two agents that work together to solve data analysis tasks using natural language. The overall workflow begins with the programmer agent writing code based on user instructions and then executing that code. We also introduce a function calling-based agent system for comparison. In our results section, we will discuss the challenges of the function calling method and the advantages of the multi-agent collaboration system. LAMBDA is built around two main agent roles, the programmer and the inspector. The programmer is responsible for generating code, while the inspector evaluates it. When a user provides instructions, the programmer writes code based on those instructions and the dataset. This code is executed in the host system's kernel environment. If any errors occur during execution, the inspector steps in to suggest improvements. The programmer then revises the code based on this feedback and resubmits it for evaluation. This iterative process continues until the code runs without errors or a predetermined maximum number of attempts is reached. To enhance reliability and flexibility, we have integrated a human intervention mechanism into the workflow, allowing users to modify the code directly when necessary. We will illustrate the collaboration algorithm in our upcoming sections. Section Summary. In this section, we explore the integration of function calling, code interpreters, multi-agent collaboration, and retrieval augmented generation, RAG, in enhancing LLMs for data analysis tasks. We propose a multi-agent system, LAMBDA, where a programmer and inspector collaborate iteratively to generate and refine code based on user instructions, while addressing challenges such as complex API interactions and the need for human intervention to ensure reliability and accuracy. Section: Programmer. In this section, we discuss the role of the programmer and the inspector in our system. The programmer's main job is to write code and interact with the user. When a user uploads their dataset, we receive a specific system prompt that details our responsibilities, the context we are working in, and the input-output formats we need to follow. This prompt is enhanced with examples to help us learn quickly. It includes information about the user's working directory, where the dataset is stored, the dataset's dimensions, the names and types of each column, any missing values, and a statistical overview. Our workflow as programmers can be summarized in a few steps. First, we write code based on the user's or inspector's instructions. Next, we extract code blocks from our output and run them in the kernel. Finally, we create a final response based on the results of the execution and share it with the user. This final response includes a summary and suggestions for the next steps. Now, regarding the inspector and the self-correcting mechanism, the inspector's main role is to suggest reasonable modifications when there are errors in the code execution. The inspector's prompt includes the code we wrote during the current dialog and the error messages from the kernel. The inspector provides actionable suggestions for us to correct the code. This prompt contains the faulty code, the kernel error messages, and the inspector's recommendations. This collaborative process continues for several rounds until the code runs successfully or we reach the maximum number of attempts. This self-correcting mechanism allows us to make multiple attempts in case of errors. We demonstrate this self-correcting mechanism in our figures and tables, showing that the system with the inspector significantly improves reliability. Furthermore, we integrate human intelligence with AI in our system. In addition to using the knowledge from large language models, LLMs, we enhance LAMBDA by incorporating human intelligence through external resources like customized algorithms and user models. We face challenges with general retrieval augmented generation (RAG) methods in data science, mainly due to the unclear connections between user instructions and code fragments, as well as the varying lengths of these code fragments. To address this, we design a knowledge base to store code resources. In our knowledge base, we represent it as pairs of descriptions and corresponding source code. When a user gives us an instruction, we use an embedding model to encode all descriptions in the knowledge base along with the instruction. We represent the embedding tensors for descriptions and instructions with specific notations. We calculate the cosine similarity between these embeddings to select knowledge that has a similarity score above a certain threshold and is the best match. We set the matching threshold at 0.5. The knowledge with the highest similarity score that meets this threshold is chosen. This knowledge is then used in in-context learning, ICL, for the LLM to generate an answer. Given a query, matched knowledge, and a set of demonstrations, the model estimates the probability of the answer and outputs the one that maximizes this probability. By integrating this knowledge through ICL, we effectively combine retrieved knowledge with contextual learning, allowing us to provide informed and contextually relevant responses. In summary, this knowledge integration mechanism enables LAMBDA to handle customized data science tasks and offers the flexibility needed to tackle complex data analysis challenges. Section Summary. In this section, we describe the roles of the programmer and inspector in a collaborative coding environment, where the programmer writes code based on user instructions and the inspector suggests modifications when errors occur, facilitating a self-correcting mechanism. We also explain how LAMBDA integrates human intelligence with AI by utilizing a knowledge base to match user instructions with relevant code resources, enhancing its ability to perform customized data science tasks effectively. Section: Report Generation. In this section, we discuss how LAMBDA can create analysis reports based on the history of dialogues. These reports typically contain data processing details, visual representations of data, descriptions of models, and evaluation outcomes. We provide a variety of report templates for users to choose from. LAMBDA generates reports in the format requested through in-context learning, allowing users to focus on more valuable tasks instead of spending time on writing and formatting reports. A sample case is illustrated in the accompanying figure. Overall, the combination of the programmer agent, inspector agent, self-correcting mechanism, and human involvement gives LAMBDA a solid theoretical foundation. The integration of knowledge makes LAMBDA both scalable and adaptable. Additionally, to enhance portability, we offer an interface similar to OpenAI's style. This means that most large language models, once implemented through open-source frameworks like VLLM and LLaMAF Factory, can work well with our system. We provide some prompts and examples in a later section. In our experiments and results, we first confirm the assumptions regarding the function calling method. We also conducted an ablation study on LAMBDA to assess the impact and performance of each agent. Finally, we evaluated LAMBDA's performance on several machine learning datasets and examined whether human intervention was necessary during the process. Regarding the challenges of the function calling method, we estimate the maximum number of application programming interfaces, APIs, that certain open-source large language models can manage in data science scenarios, based on the average length of the APIs we defined. The results are shown in a figure. Models like Qwen 1.5 and Mistral v0.1 are specifically designed to handle long sequences, managing 400 and 372 APIs, respectively. However, general-purpose models such as Llama 2, Llama 3, Mistral v0.2, Qwen 1, ChatGLM2, and ChatGLM3 can only process fewer than 100 APIs, which presents a challenge for applications that require more APIs, like data science tasks. To explore how the number of APIs affects the accuracy of LLMs in selecting them, we created a dataset of 100 commonly used APIs in data science. Using few-shot learning, We generated 880 testing instructions aligned with these APIs using Qwen 1.5 to 110b. We then divided both the APIs and testing instructions into groups of 10 for analysis. The details of the evaluation dataset are provided in a table, and the results are shown in another figure. In summary, the function calling method has several notable drawbacks. First, the process of defining many APIs is labor-intensive and inefficient. Second, the static nature of APIs limits their adaptability to changing user needs. Third, extensive API annotations can take up a significant portion of the input sequence, risking truncation. Lastly, as the number of APIs increases, the model's accuracy in selecting the correct ones decreases, which can lead to inaccuracies in responses. For the ablation study on LAMBDA, we aim to evaluate the reliability and performance of each agent using a heart disease dataset that contains missing values, which naturally presents challenges. We used Qwen 1.5-110b to generate instructions for related tasks, resulting in 454 instructions after filtering. We assessed the execution pass rate for a single programmer agent and for multiple agents, the programmer and inspector, separately. The results are summarized in a table. The findings reveal a significant difference in the passing rate between using just a programmer agent and including an inspector. The programmer agent alone achieved a passing rate of 68.06%, while adding the inspector raised the passing rate to 95.37%, showing a substantial improvement of 40.13%. This experiment confirmed the essential role of collaborative agents in enhancing LAMBDA's reliability and robustness. By leveraging their complementary strengths in suggesting and correcting errors, the multi-agent collaboration approach not only boosts the code passing rate but also reduces the need for human intervention in complex data analysis tasks. In our experiments on machine learning datasets, we sought to gain practical experience and assess performance in real-world data science tasks. We recorded LAMBDA's performance on these datasets and noted whether human involvement was necessary. We used accuracy as the evaluation metric for classification tasks and mean squared error for regression tasks. The results are presented in a table. We evaluated several datasets, including the AIDS Clinical Trials Group Study 175, which provides healthcare statistics and categorical data on AIDS patients, and the National Health and Nutrition Health Survey 2013-2014 Age Prediction Subset, which focuses on predicting age groups based on various health data. Other datasets included breast cancer Wisconsin, diagnostic, wine chemical analysis, concrete compressive strength, combined cycle power plant performance, abalone age prediction, and airfoil self-noise prediction. The results demonstrate LAMBDA's strong performance in executing machine learning tasks. For classification tasks, LAMBDA achieved high accuracies of 89.67%, 100%, 98.07%, and 98.89% for the AIDS, NHANES, breast cancer, and wine datasets, respectively. For regression tasks, it recorded the lowest mean squared errors of 0.2749, 0.0315, 0.4542, and 0.2528, respectively. These results highlight LAMBDA's versatility in handling various data science scenarios. Notably, there was no need for human involvement throughout these experiments, demonstrating that LAMBDA effectively bridges the gap between data science and individuals who lack coding expertise. In conclusion, the experimental results indicate that LAMBDA can function as an efficient and reliable data agent, assisting people across different industries in managing data science tasks. Section Summary. In this section, we describe how LAMBDA generates comprehensive analysis reports from dialogue history, including data processing and visualizations, while allowing users to focus on high-value tasks. We also present our findings from experiments on various machine learning datasets, demonstrating LAMBDA's effectiveness in executing tasks without human intervention, thus bridging the gap between data science and users lacking coding expertise. Section. Examples. In this section, we provide 3 examples to showcase how LAMBDA excels in data analysis, integrating human intelligence and supporting education. For data analysis, we simulate scenarios where we ask LAMBDA to perform various tasks such as preparing data, creating visual representations, and training models using the IRIS dataset. LAMBDA consistently delivers accurate results. Additionally, it generates a comprehensive analysis report based on all the instructions we provide. In the area of integrating human intelligence, we illustrate how LAMBDA computes the nearest correlation matrix using a method known as the quadratically convergent Newton method. We first highlight the limitations of GPT-4 in handling this task, which emphasizes the advantages of using LAMBDA instead. Lastly, we explore an educational scenario where a teacher utilizes LAMBDA to design the curriculum, while students use it to complete exercises based on the abalone dataset. This approach enhances the efficiency of both teaching and learning.